Welcome to the Southern Plains Climate Science webinar series, which is a joint initiative of the South Central CASC, NOAA's Southern Climate Impacts Planning Program, and the USDA's Southern Plains Climate Hub. Today, I am pleased to introduce Dr. David Moeser. Dr. Moeser is a hydrologist for the New Mexico Water Science Center. Through the South Central CASC's award competition, he received funding to develop and implement novel characterizations of forest canopy as well as snow modeling tools in order to quantify the effects of canopy disturbance on snow water resources, which he will discuss further with us today. Welcome, Dr. Moeser.
Once again, I'm David Moeser, based out of Albuquerque, New Mexico at the New Mexico Water Science Center. And I'm going to talk about a changing Rio Grande Watershed, how it's potentially changed in the past and how it may change moving forward in the future, looking at two different modeling perspectives. One is a high resolution perspective, or what I would call a very hyper resolution perspective, 1 meter in resolution, looking at the changing landscape, or specifically how changing forests may modulate water in this region. Second, a coarser resolution modeling study where we use the in-house USGS PRMS model, or precipitation runoff modeling system model, to look at a changing climate moving forward to 2100. So to start off, to make sure we're all on the same page, I'm going to give you all a couple key facts, or what I think are really interesting and impactful facts to know before we move further in this presentation. First, I'm going to be speaking of just the upper Rio Grande watershed, which starts more or less around Creede, Colorado. Durango, Colorado is just, what would that be, southwest in the Four Corners region, rolling to Fort Quitman, Texas, which is north of the Big Bend in the Rio Grande. Encompasses about 32,000 square miles, so it's a very large watershed in terms of superficial area. And what makes it unique is the majority of the water originates as snow, and it falls as snow in fairly small areas relative to the total surface area of the watershed. 75% of it can originate from snowpack in these smaller regions, these headwater regions, specifically the San Juan Mountains of Colorado and the San Gabriel Cristo Mountains, Colorado, New Mexico. I should also state that the majority of the water or the snow that falls in these areas falls in primarily forested watersheds. And we'll talk about that more here in a couple minutes. The river is extremely managed, and it can go dry some years. It is over allocated most years, in fact, despite even drawing water from the Colorado side, from the San Juan Chama project that headwaters the San Juan River. Water is drawn over to the Chama River, which then leads to the Rio Grande. Here are some pictures. This is one of my favorite pictures, one of my colleagues' least favorite pictures of the Colorado-New Mexico state line. I like it because it kind of paints really a drastic picture. A whopping, I believe, when I took this picture, 10 CFS was rolling down the river, and you can look north and see the Blanca Massive right here. This is a picture I stole from New Mexico PBS online, showing a dry Rio Grande around Albuquerque. And finally, this is really kind of zooming forward into this talk. This is one of the results, looking at what we call naturalized flow, or what the USGS can also call native flow. Stream flow at Fort Quitman, at the southernmost point of the upper Rio Grande watershed, has undergone a 95% reduction in flow relative to the river's native state. So I'm going to leave you all with a couple questions before we really move forward. And we're not going to answer these questions, but I think if you have stakes in the Rio Grande watershed, these are just important questions to ponder and think about. First, are these facts, is this, from looking at these facts rather, is this sustainable moving forward? And we're going to tackle question 2 a little more in this study. What will happen if the landscape or climate changes? Will the river be even more impacted than it already is? And finally, are the small headwater regions, quote, secure? Just think, what would happen if the landscape changes in these areas? What happens and what would happen subsequently to the downstream water resources moving forward? So we're going to jump right into this high resolution study, coming primarily from this principal outputs with this long-winded title here, estimating the effects of forest structure changes from wildfire and snow water resources under varying meteorological conditions. This is a very pointed title for a specific group, so I figured I would try to simplify things and call it Canopy Structure Controls on Snow Water Resources. And I define canopy structure as the orientation of one canopy element, or you can think just one tree, to the surrounding forest. And then I was going through this presentation and realized that's also really not getting at the heart of it. So hopefully 3 times is a charm. What we're going to talk about is right here. What will happen to the snow if the forest changes? And this is fairly impactful in this region. The Rio Grande National Forest is 560,000 acres. Of those 560,000 acres, 500,000 acres have already been affected one way or another by the bark beetle. Forest fire is a major issue throughout the Intermountain West, as we are all familiar, and it is projected to increase. The National Research Council has a shocking statistic out stating with a 1 degree C increase in mean global temperature, forest fires in the Colorado headwaters and the Rio Grande headwaters are projected to increase 300 to 700%. So once again, we're going to look at what happens to the snow. This is our primary mechanism for downstream water resources in the Rio Grande if the forest changes and potentially continues to change. So we had a primary research question being, can we discretize the forest into some sort of a generalized geometry to describe locations with changes in snow water resources after a disturbance? This disturbance came in the form of a forest fire, Los Conchas fire, which we'll talk about more in a minute. And this generalized geometry, or what I would state here, basic building blocks, are these very generalized structure classes that we can break the forest up into the most basic level. So we have forest openings, or what I call forest gaps, the edges of those forest openings or the edges of those forest gaps, and finally, everything else, the interior forest. So this work took place just west of Santa Fe in the Jemez Mountains and looked at the Los Conchas fire, which I believe took place in 2011. And we were able to perform this study specifically looking at the effects of Los Conchas fire because we have pre-fire LiDAR data and post-fire LiDAR data. LiDAR is light detection and ranging data. This is aerial data. And this is how we are able to quantify a variety of metrics regarding the land surface, as well as the forest in terms of forest density, forest structure, etc. Here's some aerial imagery that lines up with the LiDAR data. Just note kind of the catastrophic nature of the fire. Here is a picture on the ground in the field area. The other thing to note here is what I call a radiation dominant area. This area is located at a low latitude, high elevation, which is fairly unique for a snow dominated area as well. You can see that radiation dominance by a decent amount of snow in that southern aspect and no snow, a decent amount of snow in that northern aspect and no snow in that southern aspect. Excuse me. So I believe 1 or 2 more introductory slides, and I promise we will get into it. I want to make sure we are all on the same page for what happens when snow falls in a forest. This is what I call an idealized SWE curve. SWE is snow water equivalence, or the amount of water in snow. And in general, we have this accumulation arm up to some sort of a peak SWE. We can find a date onto that peak SWE. And then we have this ablation arm, or this melting arm, to when all the snow melts off the landscape. And accumulation is very much dictated, or we could say governed, by the mass balance. So think when snow falls in the forest, it's going to fall, it's going to hit those canopy elements, and that snow is either going to be sublimated or unloaded into the subcanopy and distributed by a variety of processes. And it becomes extremely heterogeneous, the subcanopy snow, that is. When snow first starts falling in the picture, that is a representation coming from picture A here. That pattern is dictated by that canopy structure, or that canopy gap that it falls in. Picture B is an agglomeration of mass balance effects. It's fairly low resolution picture. I apologize. There's an old colleague of mine standing on about 1.5 meters of snow on the left here, and on the right, there's a gentleman underneath the canopy standing on very little snow. So snow, the heterogeneity of that subcanopy snow is initiated during this accumulation arm. We then hit this maximum, and that snow begins to melt. And that melting snow or that ablation arm is governed very much by the energy balance. So think that big orb in the sky shooting down shortwave radiation energetics, hitting that canopy, that energy stored as heat, potentially going into that snowpack, creating even more heterogeneity. An old colleague of mine, Dr. Claire Webster, she's actually here in picture B, and you can barely see her. She performed a really interesting study where she looked at what she would call the skin temperature or the bark temperature of a south-facing canopy edge. So the interface between an open or a gap and the forest. And she saw that the bark temperature could be 40 degrees C warmer than the mean ambient air temperature, which is kind of a shocking figure. That's a huge amount of potential energy to go into that snowpack and potentially melt it. Picture C is a representation of a south-facing canopy edge where this woman is standing simultaneously on a decent amount of snow and no snow. This really dynamic area of these canopy edges. Picture D is another picture of a canopy edge, south-facing canopy edge, where we see no snow on the edge, a decent amount of snow inside, and snow in the forest. So I'm a modeler. I guess I like to complicate things according to the general public, so to speak. So my main sub-goal was to find out where this ablation arm in general, outcompetes accumulation arm relative to a prior condition. This prior condition comes in the form of lost conscious fire in 2011. And where in general this ablating arm outcompetes accumulation arm, that's where you will see reductions in snow after a disturbance event, specifically after this fire. And I'm very much interested in this question. I guess you could say I'm a little bit of a contrarian. There's always been a historical assumption until really recently in the modeling world that when you remove the canopy, there's only going to be an increase in subcanopy snow. And that is just not correct, because we can go into the landscape after a disturbance event, whether that's the bark beetle, silvicultural practices, thinning the forest, or forest fire, and we can directly measure areas of increasing snow and decreasing snow. But that historical assumption is there because when you remove the forest canopy, what you're doing is you're removing intercepted snow, And intercepted snow typically sublimates, or basically snow removed from the water budget at a much higher level than snow sublimates either in the subcanopy or in the open. And because of that, this assumption is that there's only going to be increases in subcanopy snow. Models until recently have only shown increases in subcanopy snow because of this assumption and because how they represent the forest canopy. It's because they only integrate, these models until recently integrate canopy density. Canopy density can only tell you what is happening directly underneath that canopy element. And as important as canopy density, and if not more important than canopy density, is the structure of the forest, because we can have a lot of things happening beside that forest canopy element rather than directly underneath that forest canopy element. That canopy element can both shade the snow as well as augment the melting of that snow, as seen on pictures C and D on these canopy edges. So canopy structure has a lot to do with how snow melts in the forest and the subcanopy snow heterogeneity we see in the forest. So to reiterate, when you remove the canopy, there can be increases and decreases in snow. Typically, there are very much larger areas of increases, but there are locations of decreases in the snow, and that's what I focused on with this study, these areas of decreasing snow. So we used a model called the Snow Physics and LiDAR Mapping Model, or the Snow Palm Model. It's a really brilliant model created by Patrick Broxton and others in the University of Arizona. And the reason it's so powerful is that it integrates this idea of canopy shading or canopy structure. It has an algorithm which ingests changes in the solar zenith angle, directly integrates canopy elements, so we can look at how shading or the lack thereof may influence the subcanopy energy and mass balance budgets. So this picture kind of outlines that canopy elements are important because they shade it, and things happen in the forest, not just underneath the forest, but besides these forest elements. And that's really key, and that this model really hones in on that. And because of that, is able to show accurately canopy disturbance and locations of increasing snow and decreasing snow. This model was run at a very high resolution, 1 meter spatial resolution, so we can look at specific canopy elements as well. So what we did is we created more or less 2 equivalent models. We had a pre-fire simulation using the snowfall model, a post-fire simulation using the snowfall model. The only difference between these 2 simulations were how we represented the forest canopy, and that representation came from this LiDAR data, both pre-fire LiDAR data and post-fire LiDAR data. We then looked at the differential of the model simulations and how the snow changed between pre-fire and post-fire, and we compared how that snow changed pre-fire and post-fire to the change in forest structure, whether that is the change in forest density or the forest layout as a whole, in order to hopefully, here's the end game here, inform management decisions. If we can state precisely in the landscape where we will see these locations of increasing snow and decreasing snow, relate that to changes in the forest structure, we can potentially inform practices such as silvicultural practices when we need to manage these forests moving forward. So finally, here's some results from this modeling work. We're finally here. This very simple box plot is an agglomeration of basically millions of model runs, but just know 2 colors. We have a green color here. Those lines are the mean and median lines. Pre-fire is in green, post-fire is in red. The first thing, hopefully you all are noticing, is that post-fire we see increases in snow in general when we compare the mean and median lines. But more importantly than that is that this idea of increased post-fire variability. So we have areas of increasing snow after the fire. We also have locations of decreasing snow after that fire. And we can look at this spatially, might be a little more impactful. This is the model domain. This is looking at peak SWE and how peak SWE has changed from pre-fire to post-fire. 2 colors on here to note as well. I apologize, should have lined up the colors a little better, but note the blue color, which represents a reduction in peak SWE after this disturbance, and this yellow color, which represents locations of increasing snow after this disturbance. And we can look at how this variation spatially may or may not change through time. So here's the same graphic. It is an animation of this graphic. So we start having this accumulation arm building up in December here in the Jemez Mountains. And we have these locations of yellow, which represent increasing snow, and areas of blue, which represent decreasing snow after this disturbance. And those absolute values change, but those locations in general do not change. And that is an extremely important result. Because they do not change, we are able to define these locations based upon this generalized geometry or these basic forest building blocks or structure classes, which I have outlined here: forest gaps, forest edges, and the interior forest. That is, if we are able to define these in a relativistic manner, which we will get to here in a second. We'll let you all look at this animation once more. Once again, these areas of blue represent decreasing snow after the forest fire. Areas of yellow represent increasing snow after the forest fire. So if we define these structure classes in a relative manner, we can basically use these structure classes as a proxy for this idea of shading we talked about earlier, or a lack of shading. It's basically kind of gives us an idea of the potential energetics regime in these structure classes. So we define forest gaps based upon a mean local tree height. So here's a very large gap in our domain. And let's say that gap diameter is 30 meters. And let's say the local tree height surrounding that gap is 10 meters. In this example, we would give that gap a value of 3H, which is 3 times the width of the mean local tree height. So that's a decently sized gap. If we have a smaller gap, and we call it a 1H gap, what does that mean? That means we're having more potential shading of that gap because of those surrounding trees. We also define forest edges in a relativistic manner, and we define forest edges based upon the definition of the forest gaps. So a maximum value of 1, an edginess value, so an edge is the edge of this forest gap or this forest opening. Maximum value of 1 sits on the edge of a forest gap where the gap is greater than or equal to 3H. So the diameter is 3 times the mean local tree height. And these are further broken into aspect classes, so edginess to the north and edginess to the south. And hopefully you can see that these are, once again, to reiterate, potential energy classes. So this edginess to the south, if we have a large gap in front of that and a lack of shading from smaller trees right here, we have a lot of potential energy going in to melt that snow on those south-facing edges. As such, it's important to define these edges and these gaps in a relativistic manner. So to reiterate one last time, to give us a proxy for energy. So what I'm going to do next is we're going to look at 3 examples from the 3 structure classes. Remember, we have structure class of these openings or canopy gaps, a structure class of the edges of those gaps, and everything else, the interior forest. Since I'm a contrarian, I'm interested where we are going to see reductions in snow quantity or SWE and reductions in the retention time of the snow on the surface. Think meltout dates here. So this is an example of a canopy edge when we had a forest fire come in on this canopy edge, and that forest fire burns the gap south of that canopy edge. We started with a 1H gap. It's really hard to show 3-dimensional information in this 2-dimensional Zoom platform, but there is a gap on this edge. It's just shaded, so to speak, by the trees on the south side. This gap increased from a 1H gap to almost a maximum or a 3H gap, giving us, a maximum edginess value of 1. And these are the times that we will see reductions in snow quantity or reductions in peak SWE and earlier meltout dates. So for a modeler, this is exciting because despite complicated snow physics or snow process interactions, we can quantify locations of increased and, more importantly for me, decreased snow quantity and retention just from changes in the forest layout if we're creative in terms of how we define these structure classes. And this is hopefully in an intuitive example. So we have this forest edge on this small gap. That gap size increases to the south. Therefore, we have more potential solar energy coming in from the sun, therefore melting more snow in this example than that example. Here's another example. This is structure class 2, canopy gaps. This is really telling the same story. So we start with a gap. It's a 2H gap. You can't see the whole gap. I apologize because it's kind of shaded from these trees in this 2-dimensional world. And that gap increases from 2H to the maxima of 3H. And it increased in size to the south. That is the most important part here. So the distance to the south edge of the gap increased by 40 meters. So we have more potential incoming radiation here to melt the snow in this forest gap. And these are the locations in forest gaps where we are going to see reductions in snow. Prior studies have looked at changing gap size to optimize snow water resources. There's this gentleman named John Pomeroy, really kind of what I call the godfather of forest snow hydrology. And he did the study in Canmore in Alberta, looking at the exact change in forest size. But he used this idea of a circular gap. And they had a lot of money on their hands, and they performed these precise silvicultural techniques on the sides of the mountains where they would change the gap size and look at how that gap size would modulate subcanopy snow water resources. And this is really kind of an extension of his work, but it's what this is saying is more important than really changing the gap size, even though there is some value to know how that gap size increased. It's more important to know in what direction that gap size increased because we get an idea of potential energy there. So to reiterate, this is one of the few times that we will see reductions in snow when we increase the gap size. So more important than the change in gap size is the change in shape relative to an aspect. Here is our final structure class, the interior forest, and it's almost impossible to display this three-dimensional information on this 2D world, so you're just going to have to kind of nod your head and agree or disagree with me. So there is only one scenario, one very precise scenario where you would see reductions in snow after some sort of a disturbance event in the interior forest. And that is when the large trees were removed from the forest fire or thinning practices and the small trees were retained. And that circumstance, only, you would see a reduction in peak SWE and earlier meltdown dates, because this represents, first a decrease in interception, which therefore increases the downward shortwave radiation from a reduction in canopy shading. However, there's long wave radiation is maintained from this underlying canopy because the small trees are still there to distribute that energy into the snowpack. So this is the one time where we will see reductions in earlier meltdown dates or reductions in peak SWE in the interior forest. And this really comes from the interplay of not just canopy density, but tree heights and canopy density. So the take-home message from the modeler's perspective, once again, is despite complicated snow process interactions, we're able to quantify locations of increase and decrease snow quantity retention from some kind of a disturbance event from generalized changes in what I call forest geometry. So take-home message, I think I've said this 3 times, I guess I'll say it a fourth. Despite complicated snow physics, we're able to quantify locations of increase and decreasing snow quantity and retention just from changes in the forest geometry. And more specifically is that the change in forest shape is much more in the change in the forest density or the size. So think the size of a gap and how that gap size changes is not as important as knowing what direction that gap size changes. And knowing whether the density, which will always be reduced after disturbance, is important. It's more important to know how the forest structure changed because snow melt takes place not just underneath the forest, but besides these forest structure elements. So basic relations between snow and geometry, we can use these information to assess potential disturbance effects over larger domains and help potentially guide silvicultural practices. Think when we need to manage a forest, how can we avoid reducing snow water and potentially optimizing snow water practices? So that's all I have, I believe, for the fine scale modeling exercise. And we're going to jump right into this coarser scale model. This example, we used the precipitation runoff modeling system, the PRMS, kind of this box in-house USGS model. And we created a model of the entirety of the upper Rio Grande watershed to look at streamflow response to potential changes in climate. And this is really answering the question, what will happen to streamflow volume, the cumulative volume, and the timing of the streamflow if the climate changes through time? So here's our kind of very basic workflow here. We first calibrated a model for the entirety of the upper Rio Grande Basin. I'm going to spend a couple slides on this. It's a fairly unique way we calibrated it. And from this model, we then forced this model with data from 3 GCMs to represent representative concentration pathway 2.6, which represents the scenario for stabilization, RCP 4.5, which represents a scenario for mitigation, and RCP 8.5, I guess formerly known as business as usual, which really represents a scenario for emissions with no implemented climate policy. This is coarse resolution data, so we needed to downscale this data to better fit our local watershed here, and we integrated 3 downscaling methods, and this gave us an ensemble output of 27 potential model runs, stemming to 2,100. We then parsed the output from this model input that was fed into PRMS. We got the output. We parsed all 27 of these ensemble members into a historical time period and 3 future time periods. And we then took the difference between the historical time period and the 3 future time periods. So we calibrated this model. to represent naturalized flow, or what we at the USGS would sometimes call native flow, which is really a flow regime without anthropogenic effects. Think no withdrawals, diversions, etc. And it was a unique challenge. This is a large, highly managed watershed. So first, what we had to do is define subbasins within the basin that had little to no water withdrawals, as well as had some sort of a USGS gauge or state of Colorado or IBWC gauge with a significant period of record. So we found 9 of these subbasins. And what we did is we created a unique model for each of these 9 subbasins. And we performed a sensitivity analysis individual to each of these subbasins. And then we calibrated the model with the appropriate model parameters that we derived from the sensitivity analysis for each near native subbasins. To reiterate, leading us to 9 unique models to represent naturalized flow. And what made this calibration unique was how we then distributed these ideas that we derived in these 9 near native subbasins to the surrounding domains. We did not just distribute the parameter values that we got from this calibration, but we distributed the relationships from these calibrated values in these near native subbasins to the surrounding domain. And these relationships were based upon physical properties unique to each near native subbasin, such as soil type, elevation, slope, canopy density, etc. So we started off kind of with 1 foot forward. We used the National Hydrologic Model, which is a PRMS model for the continental United States, calibrated for the continental United States. But we needed more of a local scale calibration that precisely mimicked the naturalized flow. And here are the calibration results, or basically metrics that define goodness of fit or predictive skill. This is the Nash-Sutcliffe and percent bias. And we were able to significantly increase these values. So we're very happy with how we calibrated this model, and it was very well validated. And it took, a couple years. It was a very complicated area to calibrate, specifically in these southern basins, which are not snow dominated. They're very much monsoonally driven. So these subbasins could have a value of almost low to no flow, so a value of 0, and then have this spiky event coming from a monsoonal storm, making the hydrograph go up to several thousand CFS and back down to 0. So it was very hard to calibrate these very flashy storms, but we're very happy with the results that we got. And so I believe the next slide is representing the results from this model, representing naturalized flow from upstream to downstream. The upstream gauge on the Rio Grande main stem that we were using here is Del Norte, and the lowermost gauge, and I believe you all are now familiar with, is at Fort Quitman. Naturalized flow, or the model output, is in green, and what we see today in today's world is the stream gauge data, which is in gray. And note that the difference between naturalized flow and stream gauge flow more or less increases from upstream to downstream. I'm going to show you all my favorite picture, once again, of the state line gauge at the Colorado-New Mexico line. Just note, once again, the kind of lack of water in the mighty Rio Grande flowing through here. And I'd like you to kind of wax poetic with me for a minute and think about what it would be like back in the day when we potentially had upwards of 10,000 CFS rolling through the stream breach. And really just a different picture that we see here, looking at how stream flow was before management occurred in this basin. I also need to highlight that naturalized flow also does show very much low flow. Look at where this, at the Colorado state line, for example, naturalized flow lines up with the stream gauge, and we see flow very close to 0. However, what is striking about today's scenario is when we see low flow during times where we historically have seen very high flow, at least as the results of this calibrated model of naturalized flow show. So Here is one last graph, and it is going to look at the absolute value, the absolute difference between this green line or naturalized flow and this gray line here. It's another way to kind of visualize what we're looking at now. So from upstream is in blue, here is Del Norte. We see little difference between naturalized flow and observed gauge flow going down to Fort Quitman, and green, where we see the largest difference between naturalized flow and stream gauge flow, which makes sense. We see more change from upstream to downstream in terms of management. And this shows more or less a 95% reduction in naturalized flow in this graphic. So we're going to switch gears, and we're finally going to look at some results. So we are going to use this model of naturalized flow, and we're going to force this model of naturalized flow with future climate scenarios running forward to 2100. We're first going to look at stream flow timing. And on the, I guess we could call this the x-axis here, RCP 2.6 represents a scenario for stabilization. 4.5, mitigation. 8.5, emissions with no implemented climate policy. And the 3 future time periods are here on the y-axis. These lines represent stream reaches or stream segments. And what I want you to focus on are these areas of red, these stream segments that are red. That represents earlier stream flow timing, and in some cases, substantially earlier stream flow timing. First thing to point out is that despite time period or RCP in the headwater regions, that would be these regions here, where the majority of the stream flow is generated, regardless of RCP time period, we see significantly earlier stream flow time. For Quitman, the outlet point is more or less affected with earlier stream flow timing in all of these future time periods and scenarios. It does not become significant until the second time period. And when we get to RCP 8.5, at the latest future time period, we have a month differential of stream flow time. Stream flow timing was much more affected than volume. And here is a slide laying out the data in the same fashion, looking at change in stream flow volume. So stream flow volume gets much more complicated. The story is not as clean as stream flow timing. Spatial distribution of precipitation is much more heterogeneous, basically, than the distribution of a changing temperature regime, which can easily melt that snow and change timing more than volume. My neighbors decided to blow their lawn right now at the precisely wrong time. I apologize for that background noise. Anyway, a stream flow volume story is a little bit more complicated. I can point out some things here. In the headwater regions, there's small increases in cumulative volume for the water year. You can see here in blue represents small increases, or depending on the color of blue. But those increases are conflated by decreases in cumulative volume in other areas. As such, at this Fort Quitman gauge here, we will see in general either slight reductions in stream flow volume or negligible effects, so to speak. The story gets more interesting, when we're looking at data for the entirety of the water year. If you break up the water year into snowmelt season and monsoon season, it becomes, very fascinating. Increases in volume during snowmelt season occur. However, we see decreases in volume during the monsoon season. So my last take-home message here is that even though we are seeing small changes in volume, small changes in naturalized flow can mean big changes for the current river state. I'm going to bring you back to my favorite picture here, where we see very little flow rolling down the mighty, mighty Rio Grande. This is a model that integrates naturalized flow, and we are seeing small changes in naturalized flow, small changes, to reiterate, can mean big changes in the current state of the river. If you have any more questions regarding the stream flow changes in stream flow volume and changes in stream flow timing, there's a website that the Texas Water Science Center made for us where you can specifically look at individual GCMs or downscaling methods, as well as specific subbasins. It's an interactive website and a really great tool that I would urge you all to go to if you're interested in this. So, conclusion, basically from general to specific, as we know, the Rio Grande has changed. It's changed significantly, and we know more change is projected. My gracious, these guys are very loud. Projected future changes are primarily from a changing snow regime, and these changes are occurring in small, primarily forested watersheds. The forests in these watersheds, they're changing very rapidly. However, we can use forest geometry to potentially assess forest changes and guide silvicultural practices. Small changes in naturalized flow can lead to large changes for the current river state. Stream flow timing, as we just looked at, may change more than volume in the future, and changes in stream flow timing may be greater than 1 month. So I thank you guys for your patience. I apologize for this guy with this really loud and obnoxious blower just outside my window right now. I hope it's you all can't hear that. But to end, and before I open it up to any questions, if you have any time, I really want to give a shout out to my co-authors and funding bodies. Once again, I'm David Moeser. Shailene Chavarria played a seminal role in helping with the calibration of the model, as well as the integration of these climate data sets into this calibrated model. Graham Sexton is a snow hydrologist at the Colorado Water Science Center, helping with the snow hydrology piece. Specifically, we have a new funding for the South Central Climate Adaptation Science Center, where we are really kind of putting these two pieces of the puzzle together, this high resolution modeling scenario with the coarser resolution model, by trying to improve the representation of canopy structure in coarser scale models. Adrienne Wooden, she is a climatologist, and she provided us these climate data sets that we used and ingested into this calibrated PRMS model. Patrick Roxton was the creator of that snow physics and LiDAR mapping model, or SNOWPalm model, a really great model. Adrian Harpold, a colleague from the University of Nevada, Reno, helps me think about the output of SNOWPalm, and the three of us thought about how to better use SNOWPalm to integrate what we call these kind of critical areas in the forest landscape for changing snow. South Central Climate Adaptation Science Center has been my primary funder, with subsequent funding coming from the New Mexico Water Science Center, Corps of Engineers, and the Bureau of Reclamation. So thank you all, and thank you for your time, and please let me know if you have any questions.